In this video, just want to demonstrate that this 5-column left to right, top to bottom format is good for relatively complicated problems or analysis of situations as well. So I've got multiple instances of examples here. The first one is called Benchmarking Tractor Costs. It was a publication in Applied Engineering and Agriculture in 2015. This workbook, you can see here, has 3 sheets: a README and orientation, a version that's in English units, and a version that's in SI units. I will just walk through the English units version. So there is, again, a collection of all of the inputs in one place. And in this case, already there is a side-by-side scenario 1, scenario 2. This sheet does have data validation, so you can't make a change where things are documented or protected. We can change the price of fuel. So in the case of today, now diesel fuel is about $6 a gallon. Oop, not 60, $6 a gallon. Diesel exhaust fluid is approximately the same cost as fuel. And so from these inputs, and of course you can change the rest. Then there are a bunch of intermediate calculations. In this case, the purchase price, there was an empirical function that we came up with at that time where you could estimate the price of a tractor based on what type it is and how much horsepower it could generate. But in this case, there's a note that you could override that. If you had an actual price, then really, even though it's an intermediate calculation, you could override it with the actual price of the tractor. So all the calculations in this case flow top to bottom, a bunch of intermediate calculations, with the output being the annual cost for the tractor on an hourly basis, or the specific cost, which is cost per horsepower hour with and without fuel. Now this particular sheet has some ancillary calculations down below, so it doesn't fully follow the top to bottom part, because repair and maintenance costs, if you understand how they're estimated, it does depend on what year it happens in terms of the actual cost in today's dollars. So that's just an example. Let me just zoom out so you can see the whole of it. So here's a spreadsheet that is that big with the little ancillary table below. So about 40 rows of calculations, still top to bottom, left to right. The second instance of a relatively complicated spreadsheet. This one also published. This was in 2005. Computerized cycle analysis of harvest, transport, and unload systems. So let me scroll to the diagram. This is what a cycle analysis diagram looks like. It's very tedious to draw one of these and do the calculations manually, but the cycle analysis considers the time that a particular unit in the cycle, whether harvester, transporter, or unloader, is it actively interacting with another machine? Is it in transport mode? Is it aligning? Or does it have idle time? And the cycle time for each component has to add up and be the same. So you can identify how much idle time, essentially analyze the efficiency of your system. So that's the diagram. And it is tedious to do this manually. So it's a classic example of a good use of a spreadsheet. So here is the spreadsheet. I won't fully digest it, but just to let you see the 5-column, top to bottom, left to right part, there is a section of inputs that describes the crop, the harvester, the transport unit, and then the unloader in terms of the size, the capacity, how many do you have, things like that. Lots of intermediate calculations that the equations are declared over here in column E, so you can fully audit the sheet. In this case, units are very important, and they're all documented here in column D. But a lot of intermediate calculations, and then the final outputs have to do with what is the efficiency of utilizing the harvester, the transporter, the unloader, the labor. You get a system capacity for the entire system, and essentially an effective field capacity of the harvester. Theoretically it's 1, but if it's waiting a lot, it's a lot less. So again, a relatively complicated spreadsheet, in this case about 49 rows of calculations, but still logically constructed, all the inputs gathered together, flowing into intermediate calculations and outputs. This sheet also, when I released it to the public, also has a README sheet, so you can document what it is and where to get the reference. This third one is actually a tractor and implement model that considers the engine, the transmission, the tractive performance of the tractor, the implement force and power demand, all in one spreadsheet. So let's just go through this one top to bottom. So the inputs, there are a set of inputs that describe the tractor, and then there are subsections there with regard to the type of tractor, the tire type, and power, wheelbase, the sort of the physical dimensions. There is a characterization of the front axle, the tires and the load. There's a characterization of the rear axle, and then a very specific section that's specifically the engine, a set of descriptions of the efficiency of the engine, sort of the performance curve of the engine. It's a simplified model that's sort of relatively linear. And then there also is a section that describes the transmission of the tractor in terms of efficiencies and speed ratios. There is a section that describes the implement. In this case, it is a chisel plow. So how wide is it? How deep is it tilling? Characterization of the soil that it's operating. Now, in this case, because the force required to pull an implement is a function of the speed of the implement, the speed at which the tractor is pulling the implement is a function of the slip of the tractor. The slip of the tractor is also a function, in an iterative way, is a function of how much pull the tractor has to generate. Also, back to the load on the tires, as an implement pulls back on the tractor and the tractor pulls on the implement, the dynamic load on the tire is a function of the pull that the tractor is generating. So it's a very iterative problem. So in this case, there has to be some starting point. So you make a guess as to what the engine speed is, what the slip is, and the pull estimate. And then, based on those guesses, the full calculation goes. So there are a lot of intermediate calculations here that don't rely on the iteration, related to the performance of the engine, related to the traction and the transmission. Then there are some intermediate calculations that do require that iteration of I made a guess. You calculate things based on the guess, and then you refine the guess and get a little closer each time. So not to fully explain this spreadsheet, there was an ASABE paper about it that was published, but there you'll notice a lot of iterative calculations here, and then it's kind of odd, but I think you'll appreciate the creativity here. There are, as you make guesses, there will be an error in engine torque, error in speed, error in traction pull estimate, the pull of the draft, and then even though that's Newton meters, this is RPM, that's newtons, and that's newtons, we added those up, and then we actually use solver to make the error go to 0 by changing essentially those wild guesses of the starting point for the iteration. So hopefully this will be successful. If you hit solve, all the errors go to 0, and now we have the actual performance here, what the engine speed would be, the pull that the tractor is generating to match the requirement of the implement, etc. So quite a complex problem. I just want to scroll out so that you can see the complexity of it. Let's go zoom back in. So this is about 130 rows of calculations, relatively complex model that's kind of all inclusive of the engine, transmission, traction, implement, but all of it in this simple 5-column format so that the calculations can follow. There are a couple of tables over here that were used in lookup functions to find coefficients for the solution. The last relatively complex 5-column spreadsheet tool that I'll show here is something that we call the Purdue Crop Planner. And you'll see here it does have macros, so if you fetch this, you need to enable the content, which is the macros. This particular tool is complex enough that there's a relatively lengthy set of instructions on how to use it. There is also even a recorded orientation video to watch to understand how to use it. But for the purpose of this video, I will simply show the back-end tables that are used in a lookup and data validation way. There is a list of fields. So it's just called the fields sheet. There is a fields list, some documentation with notes about that it is named and how it is used. So that's the fields. There's a set of inputs. These are all in one sheet, but there is a list of potential seeds, a list of fertilizers, herbicides, insecticides, and fungicides. Then here is the real sheet. So this is a by field analysis or a by management zone analysis. So I did use conditional formatting where you can check this box and see the names of variables, and down here you can see the formulas that are used in the sheet, but I'll uncheck it. Well, I'll leave it checked so you can see them. So the idea here is that each column would be a field or a management zone. The macros allow you to add another field or delete the last field. So you describe, in this case, there are sections on the inputs, which are the name of the field, lots of things about the income aspects. There are many things about the cost aspects. Won't go through each one of them, but I will point out that in most cases, there's data validation that draws from the fields list, the inputs lists. So you first populate those background tables, because then they're going to inform all the inputs over here for seed, fertilizer, herbicides, insecticides. And the reason that there are multiples of these is you don't just put one fertilizer on a cornfield. You might put a combination of things. So that's why there are 4 different ones. So there are inputs related to cover crops, water management, the machinery, and post-harvest. And then after all of that, so this is an economic analysis, really. It's like a partial budget where you compute all these components of costs and in the end get an estimate of the return over the considered costs, whatever costs are included in this sheet. You can now say that's the return over those costs. And then in addition to the by field in each column, there is also an analysis of the whole farm. So here is a sheet that's got nominally 63 rows of inputs, intermediate calculations, and outputs. There is a data table here that conducts what I would call a sensitivity analysis. So it's essentially the profitability sensitivity to the corn price and the yield with a sort of a baseline plus or minus 15% on yield and plus or minus 15 or 30% on crop price. And there's also a pie chart that's automatically populated by the data in one of those columns. So this tool, or this approach of the 5-column left to right, top to bottom, is very adaptable. You will notice if you look at this one, the units actually come before the numbers. And the reason is, if you keep adding columns, the units would be off to the right and you might not remember what they are. So in this case, it's the abbreviation, full description, units, followed by numbers, numbers, numbers. And if a farm had 20 different fields, well, there'll be 20 different columns here. So I hope these, that was a little longer video than I anticipated, but I hope these examples help you realize that this structure is applicable to problems of many different types, of many different sort of sizes and scopes and levels of complexity. I'm Dennis Buckmaster, professor in agricultural and biological engineering at Purdue University, and I hope that this habit of solving problems in this way is one that you can gain, and it will help you communicate the solution to mathematical problems to yourself and others with clarity.